Welcome back to our algebraic graph theory seminar. And today, Chris Godsil is going to talk to us about fractional and quantum isomorphisms.
Thanks, Maria. Actually, the reason I'm talking today was last Wednesday, Sabrina, who's organised the speakers, is getting frantic, and so she had to reach further into the barrel of the bed. And that led to me giving today's talk. So here's the abstract. I'm going to talk about two generalizations of permutations or ordinals of graphs. I'm going to talk about fractional isomorphisms and quantum isomorphisms. And then I'm going to discuss a direct connection between the quantum isomorphisms and the fractional isomorphisms. So in some sense, there are three parts. So I'm going to start by talking about fractional isomorphisms. And so to do that, I need to talk about doubly stochastic matrices. So a doubly stochastic matrix is a real non-negative matrix, and each row and column sums to 1. Okay, good enough. So the simplest example of permutation matrices, they're doubly stochastic. Now, a doubly stochastic matrix is necessarily square, and the point is that if I've got a silly example here, but if I sum each column of this matrix, then I get ones. And so the sum of those ones is going to be the number of columns. Now, if I do the same thing for rows, the sum is the number of rows. And so either by the fundamental theorem of accountancy or Fubini's theorem of measure theory, the sum of the rows is equal to the sum of the column sums, and so R is equal to C. Okay. So in particular, doubly stochastic matrix is necessarily square. Now, the set of doubly stochastic matrices is a convex polytope. It's easy to check that any convex combination of doubly stochastic matrices is doubly stochastic. It's got a couple of other properties. It's closed under transposes because it's doubly stochastic, so the transpose of doubly stochastic matrix is doubly stochastic, and it's closed under multiplication. So, and since it contains the identity, it's technically a monoid. Now, I haven't seen places where these B and C get used, but so it is a convex polytope. Now, the problem with once you get a convex polytope is that someone's going to ask you questions like, what are the vertices of this polytope? Now, the doubly stochastic matrices are given to you by a set of linear equations, basically saying that sum of each row is 1 and the sum of each column is 1. So there's an intersection given to you as an intersection of half spaces, so that's why it's convex. And since it's bounded, there's going to be a convex polytope, but then someone's going to turn around and ask you, what are the vertices? Now, if somebody asks you what are the vertices of some polytope, it's generally best to run away. But in this case, we do know an answer. The first thing is that each permutation matrix is a vertex. Now, I should say that terminology vertices and edges of polytopes predates vertices and edges for graph theory. In some sense, it's where it comes from. But so a vertex of a polytope is a point in a polytope, so that there's a hyperplane which contains that point, and all the remaining points of the polytope lie completely to one side of that hyperplane. So you have a hyperplane and it meets the polytope in exactly one point. And the Birkhoff, as most of you will know, proved that the permutation matrices are precisely the vertices of the polytope of doubly stochastic matrices. I'm just going to do the easy part here. So I'm going to be using M comma N in brackets to denote, represent trace of M star N. That's an inner product on N by N matrices. Okay. Now, if I take P comma P, I'm taking the trace of P transpose P, but P transpose P is P inverse P. It's the identity. So probably there should be an N. It's not going to matter much. Okay, that's an N. Oops, that doesn't work. Let's fix it. And this should be an N. Now, the other thing you can see, and this is, as a general principle of this talk, there's going to be, the good news is there won't be many proofs. The bad news is there'll be lots of exercises. And so it's quite easy to check that if S is doubly stochastic and not equal to P, then P comma S is less than N. Okay, so that implies that each permutation matrix is a vertex. Now, the converse is what's really Birkhoff's theorem, and that's equivalent to the fact that a regular bipolar graph has a perfect matching. So we get the permutation matrices of the vertices of the polytope, so we can describe the vertices of the polytope. Okay, so that's it for doubly stochastic matrices. So now I want to talk about fractional isomorphisms. Okay, and this is really straightforward. We're given graphs X and Y, and there'll be X and Y for the rest of the talk, and adjacency matrices A and B, respectively. And then X and Y are fractionally isomorphic if there's a doubly stochastic matrix S such that AS equals SB. Now, since permutation matrices are doubly stochastic, you see that isomorphic graphs are fractionally isomorphic. So this is you can view fractionally isomorphic as a generalization or relaxation of classically isomorphic. Now, so as I just said, isomorphisms are fractional isomorphisms. Any 2K regular graphs on n vertices are fractionally isomorphic. So this is a fairly crude relation. The point here is that if X and Y are K regular graphs on n vertices, A and B, you just take S to be 1 on n times J. And then AS will be K on n times J. And SB will be K on n times J. So from a point of view of distinguishing graphs, you could say this is pretty much a failure. Any 2 regular graphs of the same plane, 600 vertices are fractionally isomorphic, but we'll see it's still interesting to think about. Another comment is, since A and B are symmetric, if AS is equal to SB, and we get that BS transpose equal to S transpose A, with the net result that this implies fractional isomorphism is actually an equivalence relation, which we're more or less assuming. Okay, so and the other comment I want to make is we define if AS is equal to SA, then S is a fractional automorphism. So this is all consistent with permutations, and no surprises really. Now, the next comment is if we're given a fractional isomorphism between 2 graphs, then we can construct fractional automorphisms. And so I've actually written down the proof here just for once. So if AS is equal to SB, then by taking transposes, BS transpose is S transpose A. And so if I multiply this on the left by S, I get SS transpose A is equal to SB S transpose, but BS transpose is S transpose A. So I get this equal to this. So SS transpose commutes with A. Now, S is a non-negative matrix and S transpose is a non-negative matrix, so SS transpose is not negative. And a square matrix is doubly stochastic if the ones vector is an eigenvector, well, both a right eigenvector and a left eigenvector. So it's SS transpose applied to the all-ones vector is just the all-ones vector. And so we deduce that SS transpose is a fractional isomorphism. It's doubly stochastic commutes with A. Now, if you chose S to be a permutation, then this would just be the identity. But in general, it could be anything. And I'm going to use curly S of X to denote the set of all fractional automorphisms of X. Now, this is again a convex set, okay, because you're just taking the doubly stochastic matrices and then adding the condition that the matrix commutes with A, and that gives you a sort of linear equation, so you get a polytope. Now, any automorphism graph will give you an element of curly S of X. Okay. But and they will be vertices, but who knows what else is there. And it's an interesting point, which I won't go into today. The graph is said to be compact if the vertices of S of X are permutation matrices. So there are no vertices that aren't permutation matrices. Now, this is a very strong condition. And it was, I think it was probably introduced first by Tinhofer. It's an interesting topic, but and I don't want to spend a lot of time. I'm not going to go into today, but it's somewhere to go. Now, the question we might ask, or one question you can ask is, okay, we've got two graphs, and they're fractionally isomorphic. What properties of this graph do these graphs what properties must these graphs share? Now, the simplest observation is, in fact, they must have the same degree sequence. Now, I'm going to state I've got a theorem here which implies more. So, if X and Y are fractionally isomorphic graphs and then vertices, there's a permutation matrix P that maps this matrix to this matrix. Now, P1 is equal to 1, or that's not a surprise, but P applied to A1 is equal to B1. But B1 is just the vector of degrees of the graph Y. And so it follows from this immediately that if two graphs are fractionally isomorphic, they have the same degree sequence. This also implies, well, this requires a little bit of work, that they have the same spectral radius. In fact, the rank of this matrix, here's my red pen again, is so the rank of this will be the number of main eigenvalues. It's main. Now, the terminology, I think, is due to Svetkovich. An eigenvalue is a main eigenvalue if it has an eigenvector which doesn't sum to 0. Okay, and so the column space of these matrices is spanned by the exactly those eigenvectors. Now, if you have an eigenspace and it contains an eigenvector that sums to 0, you can assume all the other eigenvectors do sum to 0. And so each eigenspace will give you one main eigenvector. And so we get that connection. So this is related to things called work modules that come up in quantum walks, but I won't go into that today. So, we do have this in common. I'll say a little bit about the proof. The key step in the proof, which is not trivial, is that if R and S are stochastic matrices and the vectors Y and X related to Y is R times X and S is S times Y, then Y is equal to permutation P times X for some permutation matrix P. Now, the proof of this uses Birkhoff's theorem and some cute play with convex polytopes. But there's a book by Scheinemann and Ullmann called Fractional Graph Theory, and they have a proof of that in there. This is known in various forms. It goes back quite a while. I think it's actually even in a book by Hardy and Littlewood. So from that, you can deduce this without too great an effort. And we do have time for a bit, but I won't. So the other comment I should make is, actually, no, I'm going to wait for a second about equal partitions. So I've talked about, basically I want to talk about fractional isomorphisms, fractional automorphisms now, and we get them from permutations. Now, what I'm going to do next is discuss equitable partitions, which may not be a surprise, but in this case, we're going to use them to construct more elements of curly S of X. Some notation. So I'm going to have a graph. I've got a graph X, and pi is a partition of its vertices. And a partition is a collection of sets, and so I can represent each set by a characteristic vector, and I can pack those characteristic vectors into the columns of a matrix. Now, and so I would call that the characteristic matrix of the partition. Okay, instead of having a characteristic matrix of a subset, I've got a characteristic matrix of a partition. I'm going to go one step further. I'm going to scale the column so each column has norm 1. It's entirely optional in some sense, but it's going to be convenient in this case. So here, for your edification, is a simple example. Okay, so this is a partition with cells of size 1, 2, and 3, and it's normalized. Now, if it's normalized, then N transpose N is equal to the identity, which is obvious in this case. Okay, so now the other thing that matters is, if it's normalized, is that N transpose is a projection. You can see that it's symmetric, and it's very easy to see that its square is equal to itself. So it's a projection. Okay, so that will come back to haunt us in a few seconds. And so we have the following characterization of equitable partitions. So the first is that pi is equitable, which I'm safe, I haven't defined it yet, so that's all right. The second is that the column space of its normalized characteristic matrix is invariant in the action of A. Okay, now this is equivalent to the statement that if I apply A to N, the result is equal to N times C for some matrix C of order size of pi times size of pi. Size of pi is the number of cells. Okay, so this is sort of the combinatorial definition of equitable written out in terms of matrices. And so that's the as close as I'm going to get. So the usual definition is to say we have a partition of the vertices that graph into cells. Each cell induces a regular subgraph, and the edges joining two cells form a semi-regular bipartite graph. So that's the combinatorial definition. Now, in practice, the definition B is at least as useful. Okay, but so the column space of N is the space of functions on the vertices of graph that are constant on the cells of the partition. That's the vector space, and that vector space is A invariant. Okay, this definition is useful because if you want to replace the adjacency geometry graph by, say, the adjacency Laplacian, you can still use this immediately. You don't have to try and decode what this means in that case. So, and if you want to prove the joint of two equitable partitions is equitable, and this gives you an easy way of doing it. So, but anyway, there's the characterization. And the example, of course, a canonical example is that if you have a group of automorphisms to your graph, then the orbits of that group form an equitable partition. And it's fairly easy to see that it follows from the combinatorial definition. So any orbits of the graph gives us an equitable partition. Now, I probably should say if a graph is regular, then the partition with one cell is equitable. Okay, if the graph is asymmetric, then that's got nothing to do with permutations or orbits. And so the equitable partitions are related to orbits. And in fact, Brent McKay worked a lot on equitable partitions because when he was putting naughty together, he was using properties of equitable partitions. Okay, so if you're working with graph isomorphism, you tend to be naturally led to equitable partitions. And so if all your equitable partitions came from orbits, you'd be in a very nice situation. Unfortunately, life's not so kind. So as I said, the projection of the column space of N is NN transpose. Now, I mentioned it's a projection, and it's easy to see the column space is contained in the column space of N, so there's a little bit of work left, but so that's the projection on the column space. Okay, and the point is that given that N will be doubly stochastic, now maybe I should just go back just this once. If you look at NN transpose, you're going to get a matrix with block diagonal matrix with 3 blocks. The first block will just be 1. Second block will be half the 2 by 2 all ones matrix, and the third block will be 1/3 the all ones matrix. So the conclusion, I'm calling it a proof, is that this projection, NN transpose, is doubly stochastic. Okay, and we're saying the column space of N is A invariant if and if A and N transpose commute. Okay, now this is a very important case of linear algebra. If you have a subspace of the reals or complexes, you can describe it by a projection. And for you to do more generally, you have a subspace described by a projection, then your matrix or operator A fixes that subspace if and only if it commutes with the projection. Now, this is something that they tend not to cover in the undergraduate courses, but it's not particularly difficult and it's very, very useful. Okay, so in this case, we're getting that because the cos face of n is A invariant, beginning that A and N transpose commute. And so that tells me that this doubly stochastic matrix is in curly S of X. So equitable partitions give us elements of the set of script S of X. Okay. So, and as I said, my example with the regular graphs tells you we can get partitions which we can't get from permutations. So even if the graph is asymmetric with no automorphisms, it can still have equitable partitions. Okay, and so Sx is still non-empty. So equitable partitions give rise to fractional isomorphisms. I should say one more thing before I go on. I asked the question, what was the, if we have two graphs that are fractionally isomorphic, what properties do they share? Now, there's a theorem in the book by Shineman, or one I mentioned before, for example, that says that, well, if you have a graph, okay, there's always a coarse equitable partition, so an equitable partition with a minimum number of cells. Now, if your graph's got n vertices, you could always be lazy and take the partition where each cell is a singleton. That's certainly equitable. But you want the coarse equitable partition, so you want the partition with a minimum number of cells. And so this is well defined and can be computed in polynomial time. Okay. Now, the theorem say the theorem is that two graphs X and Y are fractional isomorphic if and only if the quotient over the course of equal partitions are equal. Okay, now I spent some time thinking that implied that we could test for fractional isomorphism in polynomial time. But the way the theorem is stated is a little vague. My problem is I compute this coarse equal partition. Most of the cells could be small, so they can have lots of cells. And so I do compute the quotient for X and the quotient for Y, and I get two matrices with integer entries, and then I have to decide whether they're isomorphic. So on the face of it, I won't go to theorem, there's no easier, it's not easy to decide if two graphs are fractionally isomorphic. Okay. It is equivalent to having a common a common quotient. And interestingly enough, that's equivalent to the two graphs having a finite common cover. We don't need that, so I won't go there. So that's another relation between equal partitions and things we're thinking about. So we've seen that equal partitions give rise to fractional isomorphisms. The next interesting thing is, in fact, the converse is true. Fractional isomorphisms give us equitable partitions. Okay, so the connection is closer than just another construction. Now, the way to do this is we have a doubly stochastic matrix. And so we're just going to think of it as a weighted adjacency matrix of a directed graph. Okay. So, well, then the result I need, which is through graph theory, because S is doubly stochastic, the weak components of this directed graph are the strong components. So if you can get from one vertex to another, so weak component means you can get from one vertex to another by a sequence of arcs, and you don't care about directions. You're not going to obey the one-way street signs. Okay. Strongly connected means that you can get from one vertex for any pair of vertices A and B. You can get from A to B by following the street signs, following the one-way signs, and coming back again, because you can get from B to A. So where the claim is that this is, if we're doubly stochastic, then any weak component is strong connected. So basically, we don't need to worry about whether our components are weak and strong. I mean, another way of thinking of the weak components is that if you have this, they're the components of the underlying directed graphs, undirected graphs. So if you've got a directed graph, you define a new graph with the same vertex set, two vertices are adjacent. If there's an arc joining them, don't care about direction. Okay, so the components of that graph are the weak components. Okay, and the strong components are defined as I just did. Okay, so that now there's a related result which I've used, namely if a bipartite graph has got isolinear, if the in degree of each vertex equal to the out degree, then again you can prove that the weak components and strong components coincide, and this is closely related to that. if you imagine you've got your matrix and you've got a weak component, so you've got something like this with stuff, 0, and the diagonal block's a square. Then the sum of the columns in that group are all equal to 1. And so when then you work out the sum of the row sums, well, it has to be equal to the number of columns, and so that forces the sum of the row sums to be equal to 1, and that forces this to be 0. But as I said, I wasn't going to give you many. There's not going to be any proofs. There's going to be lots of exercises, and this is a nice one. And it's not too hard. So the point is that if we have a doubly stochastic matrix, we can always put it in block diagonal form. Okay, where each block corresponds is a weighted adjacency matrix of a strongly connected vector graph. Now, and so I'm using the word irreducible instead of strongly connected. And of course, there are terms in decomposable and irreducible which you can throw around. We don't need to worry about the difference because in this case they coincide. Okay, so the theorem we throw at this now is going to be the Perrin-Frobenius theorem. It says if you have a square non-negative matrix and it's irreducible, then the largest eigenvalue is simple. And that's part of the Perrin-Frobenius theorem. The Perrin-Frobenius theorem is really a connection of about 3 or 4 theorems, and it's never quite clear which one you mean when you say you're using it. But it's certainly part of the Perrin-Frobenius theorem is that the largest eigenvalue is simple. So in this case, that means the current polynomial has 1 as a simple well, t minus 1 as a simple factor. So, well, what does that do for us? So each of those SIs has an all ones vector as an eigenvector with eigenvalue 1. And so each of those SIs got spectral radius 1. The strong components of S partition V of X. And if F is the normalized characteristic matrix of this partition, then NN transpose is the projection onto the kernel of S minus I. So it's a projection onto the one eigenspace, but I couldn't fit one eigenspace in the gap there, so I wrote curve S minus I. Okay. So NN transpose is the projection onto the kernel S minus I. Now, NN transpose, where's my picture? Basically, just replace each of, if this block is M by M, you replace it by 1 on M times J. Okay, and so you do that, and so you've now got a block diagonal matrix with entries 1 on M times J. It's doubly stochastic. Okay, now the point is it's the projection onto the eigenspace of S, the one eigenspace of S. Okay, and I call this a claim because this is a doable exercise, but it'll cost you some grief. The fact NN transpose is a polynomial in S. Now, usually we prove this by using spectral decomposition. We can't use spectral decomposition because S is not symmetric.
What was S again?
What was S?
Mm-hmm. Yeah.
I'm assuming that S is the fractional isomorphism. Any other questions while we're here? Not just you. Okay. Yeah. So it's a polynomial in S. Now, if S is a fractional automorphism, then S commutes with A. And so that means that A commutes with NN transpose. Okay. And so that then follows that this partition we're dealing with is an equitable partition. And so what we've got to is that the strong components of our director graph, or the vertex sets of the strong components, form an equitable partition of our underlying graph. Okay. And so therefore each fractional automorphism gives rise to an equitable partition. Now, this is useful. I call a graph controllable if the algebra generated by the matrices A and J is a set of all n by matrices over the reals. So you're taking all linear combinations of all products of A and J. Now, this is not going to be very interesting if A is regular, but I conjectured, and O'Rourke and Turi proved that almost all graphs are controllable. Okay. Now, this is a very strong condition. It implies that almost all graphs are asymmetric, have only the identity of automorphism. It also implies that for almost all graphs, because of this result, O'Rourke and Turi, that the only equitable partition they have to admit is the discrete partition with each cell a single vertex. Now, Babai proved that a random graph doesn't have an equitable partition. I kind of like this result because if somebody gives you a graph and asks, is it random? There's not much you can do, but you can actually test in polynomial time whether the graph is controllable. So it's anyway, both approaches work. So if X is controllable, and so this tells us that S of X is trivial in most cases. Okay, if you're picking up graphs at random, then you're not going to get anything interesting. So you have to be clever on that. Okay, so I've talked about fractional isomorphisms, fractional automorphisms, and we've seen a connection between equitable partitions and fractional automorphisms. Now I want to go on and talk about quantum permutations. Now, okay, so here we go. A quantum permutation is an n by n matrix P with entries from the ring d by d matrices over the complexes, such that each entry is a projection. So it's emission and square root to identity, and the sum of each row and the sum of each column. I probably wrote it backwards, but don't worry. Those two sums are equal to the identity. Now, there are two ways of thinking about these matrices P. One is to think of them, as I've just said, as a matrix whose entries are coming from some more complicated ring than we usually work with. The other is you can think of it as an ND by ND matrix with blocks of size D by D. Okay. Generally, I find it better to use this version, but there are times when the other one's better, and so I'll use both, and you'll have to rely on the context to tell you which I'm dealing with. I'll say more in a moment. So this is a quantum permutation. So what you're doing is, well, as I said, any permutation matrix is a quantum permutation because 0 and 1 are projections, and the rows and columns onto 1. Okay. So they exist. Now, the one point I need to make, which we will need, is that this second condition here implies that the entries in each row commute pairwise orthogonal, so commute, and the entries in each column are pairwise orthogonal. Okay. Which is again true for permutation. So this is a quantum permutation. I'll say a bit more about motivation in a moment. But I want to prove that claim I just remade. So I need the fact that if Q1 up to QK are D by D projections and they sum to the identity, then the product of distinct terms is 0. Okay. And it's a nice little exercise in positive and indefinite things. So we have I is equal to sum. So I is equal to I squared. And so we get a sum of QI squared, or it's just QI because we're dealing with projections, and the sum of the products of distinct terms. Now, this term here is just I again. And so we get that the sum of the products of the distinct terms is 0. Now, it's not quite clear what to do with that. It's not obvious to do work. You take the trace. And so you get that 0 is equal to the sum of the traces of QI, QJ. Now, the point is QI and QJ are posi-semi-definite, so that the trace of their product is non-negative, and it's 0 if and only if the product itself is 0. Okay, and so that's what I need. And so there's a little exercise in posi-semi-definite matrices there, but otherwise we're complete. So if we have a quantum permutation, the entries in a given row and the entries in a given column commute. Permutation to one example. What have I got next? A few remarks. The quantum permutation is a unitary matrix. Okay, this is interesting, it's not going to play much of a role. The product of two quantum permutations is not, in general, a quantum permutation. Okay? Now, products of fractional automorphisms are fractional automorphisms. We haven't got the quantum morphisms yet, but the product of two quantum permutations is not, in general, a quantum permutation because the entries of the product will not, in general, be projections. Okay, and finally, a simple example of something which is a quantum permutation and not just a permutation. If you take your favorite n by n Latin square and choose an orthonormal basis, u1 through un, of the complex numbers, c to the d, sorry, and define p to be, well, I've written it here as, this is one of the u's times its conjugate transpose. I've decoded over here. If you assume that Lij is equal to k, then the rule is that the ij entry of p is equal to this product, uk star. Now, uk star, since these are orthonormal, uk star is a projection. Okay, and then there's a remark: if u1 through un is an orthonormal basis, then the sum of these projections is the identity. Now, that's an easy exercise. The converse is also true, and it follows from my proof that I gave, the proof that the projections in each row and each column 0, the same argument gives you that. So that u1 through un is an orthonormal basis if only if the corresponding projections are equal to the identity. Okay, so now, okay, so what are we waiting for? Quantum automorphism. So a quantum permutation is a quantum automorphism. Well, our graph is n by n, and our quantum permutation is in general nd by nd, so we can't just say multiply. So the rule we use is that a tensor id and p commute. Okay, and so here I'm thinking of p as a block matrix. I'd probably prefer to think of, replace this by some sort of a tilde, and then just say a tilde and p commute. But anyway, so this is a definition, and you can't argue about it. This is the definition of quantum isomorphism. Now, the history of this was Dave Roberson was interested in questions about isomorphisms, and became interested about getting quantum extensions. And so they were introduced in this context. So this is sort of game that's easier to see. They're a game where they say that they have, a quantum coloring is really a setup which allows two people to, in some sense, spoof referee and convince some graph is quantum k-colorable when it's not. And so they have a number of games like this, and the automorphism version of this is the quantum automorphism. And so the physicists argue this is telling you can do things with quantum technology that you can't do classically. I'm not sure why this needs extra proof, but anyway, that's the claim. So for us, at the moment, it's just a matrix, and it's not just an operation. And the motivation for us is going to be the connection to the fractional automorphisms, which we'll get to after a bit more physics. Okay, so the product of two quantum permutations is in general not a quantum permutation, but there is a substitute which we call a coproduct. And so we're defining it, coproduct of P and Q to be P star Q. And the way we do it, this is going to be a block matrix, and the ij block is going to be equal to this sum. Oops, I didn't do that. So that's a definition. And there's also a direct sum where you replace the, you take the direct sum of the two entries, one from one matrix, one from the other. And so these give you n by n block matrices. And the theorem is that if P and Q are quantum automorphisms of X, then so is the coproduct and the direct sum. Okay. So we don't have a product, we have a coproduct. The direct sum doesn't play as much of a role, but we do have a substitute for the coproduct. And that turns out to be useful. Now, the problem is, of course, that when you start taking coproducts, these get pretty big. Now, the coproduct of two permutations is just a permutation matrix. So you need something which is not just a, in fact, the coproduct of a permutation matrix with some other quantum permutation will be a quantum permutation doesn't change the size, but in general, they get pretty big pretty quickly. Okay, well, it's an imperfect universe. So the other comment I need to make is, well, the physicists tend to talk about quantum symmetries as distinct from classical symmetries, which is something, a bit of a mistake for us to go into. So if we have a quantum automorphism, if the entries of that quantum morphism commute, then you've got a collection of commuting normal matrices, and so you can simultaneously diagonalize them. Okay, so let's do that. And so now each of our projections is just a diagonal 0-1 matrix. So if the entries of the quantum permutation commute, then we can assume that the blocks are just diagonal 0-1 matrices, and the entries in each row and each column sum to I. And so it follows from this that you can express P as a direct sum of permutations, each of which commutes with each of which is an automorphism of X. So if the entries of P commute, you're not seeing anything interesting from the quantum point of view, you're just looking at the automorphism group. And so the physicists will tend to say that a quantum symmetry is a quantum permutation where the entries don't commute. Now, the problem with this is they also eventually talk about quantum automorphism groups, which I'm not going to go into. And with that setup, it follows that not every, and the quantum automorphism group contains the permutation matrices. And so in other words, the elements, according to them, of the quantum automorphism group are not quantum symmetries. So I don't much like it. So I prefer to say what you mean. So you've got a quantum permutation. If the entries don't commute, then quantum things will happen. If the entries do commute, you're back in classical. Okay, and so that's me having a little rant, excuse me. And it's easy enough to get quantum permutations where the entries don't commute. This is, I've got doing example sketched here. So we've got projections P and Q, and we start constructing this matrix. So we can reasonably extend this to a quantum permutation. The point is, if we choose P and Q not to commute, then they don't commute. So we're there. So it's not easy. It's not hard to get examples that don't commute. Now, I want to discuss the connection between quantum automorphisms and fractional automorphisms. And to do that, I have to actually bring in some physics theory. So the point to bear in mind is that when you start doing the mathematics of quantum mechanics, you're working with a mathematical model, and it has no real physical, it has no interpretations to physical. I mean, let's face it, the first step in the model is to say that the state space is a complex vector space. Now, then my question is, okay, find me a situation in the universe where I've got a complex vector space. I mean, we consider everything to be real. Okay, so the point is that, so the quantum mechanics is a mathematical model which gives you accurate predictions of what a particular experiment will do once you've set up the interpretation. But you're dealing with the mathematics, and you only get difficulties if you start thinking about what the mathematical things mean. Now, physicists say things like that a vector in R3 is more than just a triple of numbers. A vector has a meaning. And it seems to me once you ask that question, you're going down a rabbit hole. Anyway, so we just think of this in the abstract. So a measurement is just a sequence of projections, Q1 to QM, which sum to the identity. Okay, now since they sum to the identity, they're going to be pairwise orthogonal. A state is a density matrix, which is a quasi-semi-definite matrix with trace 1. Okay, and so when you do a measurement, the outcome of your measurement is basically one of the numbers 1 through m. You've got a certain number of alternatives. If you're looking at spin of electron, the outcome is either spin up or spin down. The choice is 0 or 1. Okay, so the outcome is just one of the entries 1 through m. And what the experiments will tell you is the probability that you'll observe I if you repeat the experiment. And so what the machinery of quantum mechanics is doing is telling you how to compute a probability density. So you have a probability density on 1 through m. And so how do we get our probability density? We take the trace, or we take the inner product of qi with d. Now, the inner product of qi with d is just the trace of qid. That's a non-negative, it's a real number. It's non-negative because qi and d are positive semi-definite. Okay, and if we sum over the qi's, then we get trace of I times d, but the trace of I times d is just the trace of d, which is 1. So with this definition of the outcome, we see that when we carry out the measurement, we get a probability density, okay, and the values are given by the inner products qi comma d. Okay, so let's do this. So each row and each column of a quantum permutation is a measurement. It's a collection of projections of some identity. And if P is a quantum permutation index D, and D is a density matrix of order D by D, we're defining the matrix brackets P comma D. It's going to be a matrix of reals. Its ij entry is just the inner product of Pij with D, trace of Pij times D. And so this takes out ND by ND quantum permutation and gives us an N by N matrix with non-negative entries. Now, since the Pij sum the identity, the row sum is going to be the trace of D, which is 1. So this matrix is doubly stochastic. So we have a map from quantum permutations to doubly stochastic matrices. And further, if, I said this is doubly stochastic, if P is a quantum automorphism, then the matrix P comma D will commutes with the adjacency matrix. Now, this is just plain old-fashioned matrix computation. This is commuting. This is an N by N matrix, and the adjacency matrix is N by N. And so we actually have an element of curly S of X. And okay, and interestingly enough, it works nicely with respect to the operations of coproduct and direct sum. So in particular, if we take the image of P1 star P2 relative to D1, D2, the result is the product of the two doubly stochastic matrices. And if you work with the direct sum, you get a convex combination of the two matrices. And so this tells us that the set of images we get is a compact set, sorry, is a convex set. Okay. This one tells us it's closed on the multiplication. You can check it's also closed on the transposes. And so this is something where I just said that these images form a monoid, which is transpose closed. And the coproduct operation on the quantum permutations is now a product operation on the doubly stochastic matrices. And to finish the talk, there's a few things we can prove from this machinery. Now, most of these things I think are all known to David Robertson and his co-workers with different proofs. But so first thing is if the trace of if each entry of our quantum permutation has trace 1, so for example, with that Latin square construction, we would get such a matrix. And D is just that is just 1 over D times the identity, then the measurement P comma D is 1 on N times J. And so that tells you that 1 on N times J is in curly S of A, and that implies that X is regular. Okay, so if we use the Latin square conjunction to get quantum automorphisms, it's only going to work if the graph is regular. Second thing, if the graph is controllable, you can show that the only quantum automorphism is the identity. So almost all graphs have no quantum symmetry in any sense. York-Schmidt and Weber proved that most trees, emit a non-classical quantum automorphisms, and quantum isomorphic trees are isomorphic. Thanks for your attention.
Thank you very much. Any questions? Okay, so one question is, when is it precisely that when we have two classes that are fractionally isomorphic, when will they be conspectral, when will be not conspectral?
Well, you can work it out because you just have to look at what happens to the eigenvalues main. So, I mean, so in a certain sense, that if two graphs are fractionally isomorphic, they have the main eigenvalues in common, but there's no reason why the others should have be in common. And so since you can compute the main eigenvalue, I mean, you could compute the main eigenvalues, divide that characteristic polynomial, and look at what's left over. I mean, that would be one approach.
will give you cospectral crossing?
Well, not in general, they're not cospectral. I mean, any two regular graphs are fractionally isomorphic, but in general, they're not cospectral.
Yeah. Yeah, but do we know when they will be cospectral? Is a characterization?
Well, I mean, you can tell in polynomial time whether two graphs are cospectral, so it's a bit hard to go on with a better characterization.
Well, because if we have them quantum isomorphic, they have to be cospectral. So if we're looking at fractionally isomorphic graphs,
Yes,
can be
yes, yes, I didn't say that. So, yeah, if two graphs are quantum isomorphic, then they are forced to be cospectral. But I'm not, you know, I was never certainly a, you know, the quantum automorphisms give you fractional automorphisms, but there's no, the converse is not. I'm not looking at setting the converse to have much sense.
Yes.
Yeah, I mean, I haven't said all we know about any of these topics. I mean,
No.
Yeah.
It would be nice to know if there's a characterization in the fraction isomorphic and cospectral.
Yeah, but if the characterization would be compute what modules as I did, do the calculation I just described, and if they're equal, then they're cospectral, and if they're not, they're not. I mean, it's a bit like asking for a characterization of cospectral graphs.
Yeah, okay.